So today we discuss another classification method from machine learning. Last time we spoke about k nearest neighbors. We have seen that this is quite simple idea, and the idea is based on the fact that we know some predictors, like some independent variables or features for an observation. And we know that this observation or instance belongs to some class. Like that time it was a person who had a default on a loan and who doesn't have a default on a loan. And then we know, for example, what income, age, and then when the new instance arrives, when the new borrower comes, then we compare these metrics in income and age with those who are already in our set. In our data, we measure the distance of this instance from the other instances, and then we predict whether this person is likely to default or not. Today we will do something similar, but I think you will see that this model is going to be applied under slightly different conditions. And probably this, as I said, k nearest neighbors is also applicable to predict some quantitative variables. So instead of default or not default, we can predict some numeric variable like, I don't know, the income of a person or the number of kids, whatever. So some numerical outcome. In this case, we mostly concentrate on some categorical outcomes in the case of naive Bayes, and you will see. So first of all, I think you are somehow familiar with this name, Bayes, right? So you know this from probability, and we've been discussing the Bayesian theorem, a Bayesian rule for calculating the conditional probability. So we will start with this. Yeah, so let's make some repetition. Let's start with some repetition from the probability. So first of all, let's repeat what is the conditional probability, because we really need to understand this concept and we really need to remember this concept today. So conditional probability is calculated in the following way. So a conditional probability of an event A given that an event B has occurred is equal to, so here in the numerator we have a probability that both A and B occurred together. And in the denominator, we have the probability that B occurred unconditionally. So, of course, this probability must be greater than 0, because we cannot divide by 0. Yes, let me remind you that we call this symbol P A given B. It's a probability of A given B. So we know that B occurred, and we want to calculate what is the probability that A occurs. So for example, this is an example from our lectures on probability. We roll a die, and event A is to observe 1, and event B is to observe an odd number. Suppose that you roll a die, and someone says that there is an odd number. So you don't see what's there, but someone gives you additional information. Someone gives you an information that there is an odd number. Well, we must calculate the probability that there is 1. Probability of event A given that B occurred. According to this definition, what we must calculate, first of all, we must calculate what is the probability that 1 and odd number occurred together. And this is 1 over 6, because out of 6 numbers, 1 and odd number together occurs only in 1 of out of 6 possible outcomes, right? And probability that the odd number occurs is 1/2 because they're odd or even numbers. Like 1, 3, and 5 are odd numbers, 2, 4, and 6 are even numbers. So a probability to observe an odd number is 1/2. Therefore, we calculate this as 1/3. This is the conditional probability to observe 1 if we know an additional information that odd number is there. Look, I hope that at this moment, after a long way of studying probability, statistics, and econometrics, already you can get an idea that when we want to predict something, we have some information, variables x, and we want to predict a variable y. So that's exactly what is applied here. Give me some characteristics of an object, like b, and I will give you some prediction about the outcome of an interest, probability of A. So we will use this rule for making predictions. So before that, let's let's try to remember what is the bias rule. We have one event A, and we have several events B, B1, B2, B3, up to Bn, such that they are disjoint. So disjoint events cannot happen simultaneously. So disjoint events, so their union equals to the sample space, sigma, omega, sorry. So probability of each of these events is non-zero. And so here is the formal definition of the bias rule. So let's try to understand this backwards. Let's try to remember what does this mean. So probability of bj given A, so I know that A has occurred. What is the probability that bj occurs? Equals to here, first of all. So this object is taken from the previous slide. So this is a conditional probability. The probability that A and B, J occur together over probability of A. So nice. We borrowed this from the previous slide. Now, how to calculate this probability that A and B occur together? We must, again, basically we use the same formula. What is the probability that A and B occur together? We multiply probability of A given B by the probability of B. But we also can reverse this. We can take probability of B given A multiplied by the probability of A, and that's exactly what we do here. Look, we take probability of A, so we don't know what is the probability of B given A, but we know what is the probability of A given B and probability of B. And we multiply them, and we get this probability that A and B occur together. So I will give you an example just for a reminder, and I hope you will understand how this works. In the denominator, we calculate the total probability that event A occurs. So event A occurs when B1 occurs, when B2 occurs, when B3 occurs, and so on up to Bn. So therefore, we calculate the sum of these probabilities. So for those who want to remember this better, there are recordings of our probability lectures, so please rewatch the lecture number 4 from probability. Let me give you an example to understand how this works, and this would be very nice if you understand and you feel very free in using this bias rule or bias theorem. So there are different names of this formula. So let's give the following example. So let S be the event the message is spam, so the email, and B the event the message contains the word Bitcoin. So it means that the machine recognizes, reads the text, and recognizes, so there is a word Bitcoin. And machine somehow must automatically assign whether this email is spam or not. So before doing this, of course, we need to understand how to apply the bias rule here. So suppose we know that the probability to receive a spam email is 0.3. So PS. Probability to receive a spam email with the word Bitcoin is 0.5. So what does this mean? Out of all spam messages, so given as, right? So it means that we restrict our universe to the emails which are spam emails only. And out of them, probability to receive a spam email with containing the word Bitcoin is 0.5. And probability to receive an email which is not spam, so this is SC, which is spam complement, right? So not spam. So probability to receive not spam email containing the word Bitcoin is 0.01. So look, in principle, I can receive a message with the word Bitcoin in two different cases. In the one case, it is gonna be spam, and I know that the probability of this is 0.5. In the other case, I can receive also, like suppose that some friend writes you an email and asks you about how Bitcoin works, knowing that you are an economist and you can explain all these things. This is not a spam, definitely. So probability to receive such letter that contains Bitcoin but not a spam is 0.01. And look, the total probability to receive a letter with a Bitcoin must be calculated according to this rule here in the denominator. So let's see how this works. So now we want to calculate what is the probability that given a word Bitcoin, this letter, this email is a spam. So we want to reverse this conditionality. I know that conditional on spam, probability to receive a letter with Bitcoin is 0.5. But now I want to calculate what is the probability that I received a message and this message contains a word Bitcoin. What is the probability that this message is spam? You see that I reverse this conditionality. Instead of this, which I know, I want to make this, which I don't know. So how to calculate this? Look, in the numerator, we need to calculate the probability that both A and B occur. So what is A and B? In our case, both spam and Bitcoin occur. So how to deal with this? I know that the conditional probability to to receive a message with Bitcoin given spam is 0.5. And I know that the probability to receive spam is 0.3. So which means that the total probability is gonna be 0.5 times 0.3. Probability that I will receive spam and probability that I receive after receiving spam, this letter is gonna contain a word Bitcoin. So 0.5 times 0.3. In the denominator, I need to calculate the total probability to receive a letter with a Bitcoin. So first of all, I can receive a letter with a Bitcoin when it's spam, and I know this probability, it's 0.5 times 0.3, or it might be not a spam with the word Bitcoin. What is the probability that I will receive not a spam email? This is 0.7 here. And I multiply 0.7 that I received not a spam message by the probability that this not spam message will contain a Bitcoin word here. And the probability that if an email contains a word Bitcoin, a probability that this email is spam is gonna be 95.5%. Meaning that only 4.5% that this email is not a spam. So it's been a while since the probability lectures about the Bayes rule. Therefore, I decided to put it here because this is very crucial to understand the naive Bayes classificator. So look at this and ask me questions if something is not clear.
Yes, thank you very much. It's really crucial here. And so we divide here like one probability that we want to find by total um, total probability of an event. Something like
Let me
this.
give you let me give you another thing that probably looks more familiar because we have been discussing the analysis of categorical data several weeks ago. And this is somehow similar to that. Look, if you can build the contingency table or something like contingency table. So for example, look, there is spam, not spam. There is a Bitcoin and not Bitcoin. And look, I know that in total, so here is total, and here is also total. I know that the total number or total probability to receive the spam message is 0.3. So I can write here 0.3 in total. It's not a number, I mean, so it's not the frequency, but it's a relative frequency or probability. In total, I know that there is going to be 1. So what is the probability of not spam letters? It's very simple. I just subtract from 1, 0.3, and it's going to be 0.7. Okay, I don't know what is the probability to receive a Bitcoin and to receive not Bitcoin, but what do I know? I know that under in this column, the probability is 50-50. So out of 0.3, half of the letters is gonna be Bitcoin with the word Bitcoin, and half of the letters is gonna be without the word Bitcoin. So then, therefore, I just need to multiply my conditional probability that I will receive a word Bitcoin in the spam letter is 0.5 multiplied by 0.3. Okay, so it means that I can calculate the difference, and that's gonna be the probability that I will receive a spam letter without a word Bitcoin, 0.15. So this is the mutual probability or joint probability. So this is the probability that I will receive both. I will receive a spam message and containing the word Bitcoin. So this is exactly the numerator of this formula here. So now, back to this, not spam. I know that word Bitcoin occurs in 1% of not spam messages. So 1% out of this 0.7. So therefore, I take this 1% and I multiply this by 0.7, and that's my joint probability that I will receive not spam message with the word Bitcoin. It's not a conditional probability now in this table. So conditional probability is this 0.01. And finally, I calculate this difference, and this is my unconditional probability that I will receive an email which is not a spam and which doesn't contain the word Bitcoin. So in total, I must have 1 here inside of this. Now, I can calculate the total probability to receive a message with a Bitcoin word and without. So I take 0.15, I add 0.07, and what I'm doing right now is this calculation of the denominator. 0.15 plus 0.07. It's here. So that's the total probability to receive a message with the Bitcoin word. And finally, this is what? This is sum of these two probabilities. So now, look, now I receive a message, and this message has a Bitcoin. So I'm here, I'm in this line. And out of this line, I must calculate what is the fraction of this spam and Bitcoin out of this overall number of Bitcoin messages. So that's That's all. I just calculated 0.15 divided by 0.157, and that's my conditional probability. So usually when you are not very good with these formulas, I strongly recommend you to go for these tables, because these tables give you all the necessary information, and they are kind of very nice to visualize what we are doing. Because the formula itself, sometimes it confuses, and not every time you understand what must be used here. So I'm using these tables because, well, they are quite nice to illustrate the whole procedure. Okay, so this is an idea. We first derive the conditional probability to receive a letter, a spam message with the Bitcoin word. We do the same for not spam messages, and then when we have a new information, well, we receive an email. This email has a word Bitcoin. What is the probability that this email is going to be spam? So we reverse all these calculations to compute this probability. So that's the whole idea of Bayesian rule. Now, an additional thing that we also need for today's lecture is independence of events. So we know about the independence, and we use this term during many different classes when we introduce the independently and identically distributed data, for example. We use the definition of independency. When we spoke about categorical data, the chi-square test was also based on an idea of independency. So let's once again repeat what is independency. So independency is defined in this way. Two events are independent if the probability of their joint occurrence equals to the product of probabilities of their individual probabilities, probability of A multiplied by probability of B. So this is the only way how you can define the independency of two events or independency of two random variables. They're the same. So now, well, intuitively we say the following. So if I know given two events, A and B, so they're independent. If I know something about the accuracy of one, I cannot predict anything about the accuracy of the other. So it gives me no additional information. And from this, we can also build the following relations, that the conditional probability of A given B equals to the unconditional probability of A. The same story here, the conditional probability of B given A equals to the unconditional probability of B. Why? Because we can derive this from the formula of conditional probability. We just take this initial formula to build the conditional probability, and then using the definition of independence, we plug in the numerator this PA times PB. PB and PB cancel each other, and we have only PA. So that's why two independent events have this nice feature, that the conditional probability of A given B equals to the unconditional probability A. So we will need the idea of independence later today. So this is the repetition. So this is what we need to remember from our previous material in order to implement this new method of naive Bayes classification. So now let's try to understand how this naive Bayes works. If you rewrite what we have discussed before in statistical terms, we can define something like this. So probability of yj given x1 blah 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 xk equals to probability of x1 blah 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 xk given yj times probability of yj divided by the probability of x1 blah 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 xk. So now instead of a and b, I'm writing these things. So what is my a? My a is this. An event that I will observe k variables of some specific values. What is my b? J is the value of y of the dependent variable, or the variable that I want to predict. It's here, and I want to calculate the probability of event bj, or in our case, event that the variable y will take value of yj, given the information about my independent variables or
So it is the
features.
same as regressor and regressant as we had in regression line, right?
Exactly. That's the same notation as we used in econometrics, as we used in statistics. That's the same. So we have one variable that we want to predict, our target variable, and we have some variables that we are going to use in order to predict. So one slight difference that in econometrics up to this moment, we have only one regressant, or regressor, sorry, X. But later we will expand this model to the multiple regression. In our case, we have already K predictors or K regressors. That's one difference. So this is not a number of observation. No, these are different variables. So yj. Yj is a class j of an outcome variable y. So for example, we want to predict if you go to the previous example about spam. So y1 is spam, y2 is not spam. Two classes of this variable. If you want to predict default or not default, y1 is default, y2 is not default. So two classes. Basically, we can do this for multinomial variables, but still they must be more or less, so they must not be the continuous variables, or at least this performs better on the discrete variables. Like, I don't know, we want to predict what is going to be the what has like 3 or 4 classes, like where like suppose we have a student, and the student before going to the university wants to know what he or she uh, does better, and to which profession he or she must go, right? So X's are gonna be some characteristics of this person, like creativity, how well this person is in mathematics, whatever, and yj is going to be the class given that like some profession, like y1 is economist, y2 is artist, y3 is engineer, y4 is IT specialist, and so on. So basically we can do something like this. But we will concentrate on the most simplest case when y takes only 2 values, like binary variable. So x's are values of the features, like not the first but ith feature, or independent variable for some instance, right? For some observation. K is the number of features, so explanatory variables or independent variables that we use. Well, this probability in the denominator is the marginal probability or likelihood to observe these features. And this is a constant for all inputs. What is very crucial here, that denominator does not depend on the classes. So denominator is the same for the whole data set. It doesn't change. There is some special terminology. It is not the terminology from only machine learning. It is also used in statistics. It is also used in economics. In economics, Bayes rule is also used widely. So therefore, so please keep this in mind. So this pyj is a prior class J probability. So it's called a prior because before receiving some additional information about access, this is your belief, or this is the probability that yj will occur. Something like your initial belief about the probability of yj with no additional information. Then you receive additional information and then you calculate the updated belief or updated probability. So this probability of access given y is the conditional probability to observe these values from x1 to xk given class yj. So mind that all these small letters substitute some specific numbers. So x1 is 2, x3 is like 5, whatever, yj is 3, and all of these letters are numbers. And our random variables take these numbers. And finally, the result is called the posterior class J probability. So this is a prior. Before receiving an information, you believe that something has this probability, and after receiving the information, you update your belief, and this is called the posterior class J probability. So, for example, in our case, look, in this example. So suppose that you receive a letter and you have no information about this letter. You don't know what is there some special word or not. You just receive a letter. Then your prior belief that this message is spam is 0.3. So you have no information about this email. So therefore you believe that this is a spam with a probability 0.3. Now you receive an additional information. You receive an information that this letter has a word Bitcoin. And then you update your belief, and your posterior now changes to 0.95 or almost 96, 95.5%. So this is an idea. So before having some information about your object, your belief is this. But after you receive some additional information and after you know something special, how this additional information, how likely that this additional information will be received under one or the other condition, you update your belief, and now you can say, well, if before you would say, well, this is not very likely that this email is spam, because 0.3 is not a large probability. But now you say, well, it's almost 100% that this email is spam, like 95.5% that this email is spam because it contains the word Bitcoin. So this is here. This is a prior class probability, something that I use with no additional information, and then I update this probability to receive or to calculate or to compute this posterior class J probability. Well, all of these things are population things, these probabilities. And as you can guess, we need to do some estimation of these probabilities. So, how we perform the estimation? Well, we estimate these terms using maximum posterior estimation. So what does this mean? Well, the probability to observe the class yj is simply the number of observations that belong to this class divided by the total number of observations in our dataset. And this is going to be the estimator of this probability, p hat.
Is it posterior or posterior?
Oh, yeah, it must be posterior. Yes, yes, thanks. That's a typo here. Yeah, for the categorical features, we are gonna talk only about categorical features, like all categorical variables, access. This probability is a frequency of this feature in the training instances belonging to the class yj estimated as here. So what does this mean? It means that I need to count how many instances have both xi and yj, so belong together to the class yj and have this instance x. And I divide this by the number of observations under in this class yj. So I will show you an example, but I guess it must be more or less clear how this works. This is also based on the contingency tables, and in the contingency tables you have seen all these numbers. Well, n is the total number of observations in the training set. Nyj is the number of observations belonging to the class yj, and nxiyj is the number of observations with the feature xi among the class yj. So all of them are numbers. So we count how many observations or how many instances in the data in total belong to the class j and belong to the class j and have the feature xi. So an example. I took this example from another book, Dangety. So as I promised, I
Sorry,
probably can
can you
share.
go back to the previous slide for a second? Okay, that's all. Thank you.
So look, suppose that our objective is to predict whether email is spam given the word Bitcoin. So the most simplest task. Suppose we collect the data on 100 emails, like the random sample of 100 emails, and we compute the following frequencies. So now you will see the contingency of frequency table here. Look, we have 100 emails in total, and we calculate how many of them are spam and contain the word Bitcoin. So there are 3. So 3 emails are spam and contain the word Bitcoin. So the and is crucial here. 19 emails are spam and do not contain the word Bitcoin. In total, we have 22 spam emails. So 2 emails are not spam, but contain the word Bitcoin. 76 emails are not spam and does not contain the word Bitcoin, so in total 78. And in total we have 5 emails containing the word Bitcoin and 95 emails that do not contain the word Bitcoin out of 100. So as I said, it must be familiar to you from our analysis of categorical data topic 2 weeks ago or 3 weeks ago. So now let's estimate these probabilities that we want. So the prior probability that an email is spam is 22 over 100. So I calculate, so these are 2 classes. Class yj or like y1 is spam, y2 is not spam. So 2 classes. So their priors are 22 over 100 and 78 over 100. Just estimate this with simple fractions. So now, conditionals. So the conditional probability that there is a Bitcoin given spam is 3 over 22. So look, I'm taking the number of instances that are both spam and contain the word Bitcoin and divide by the number of instances in this class, in the class spam. 3 over 22. I can also do this with the help of Bayesian bias rule. But in this case, I need to compute 3 over 100. And then I need to divide this by 22 over 100. But in this case, it's still gonna be 3 over 22. So no need to do all these unnecessary steps. I will calculate this in straightforward 3 over 22. Because 3 out of 22 spam emails have a word Bitcoin. Now, conditional probability that there is a word Bitcoin given not spam is 2 out of 78 here. Now, what is the conditional probability that the letter is spam but does not have a Bitcoin? It's 19 over 22, and the letter is not spam, and the probability that the not spam letter does not contain the word Bitcoin is 76 over 78 here. So we have all the conditionals. I guess it must be clear how we compute all these probabilities, or how we estimate these probabilities, because this is an estimation. And basically, that's where the learning part comes. Because when we do the machine learning, we feed this set of the data to the machine, and machine learns these probabilities from the data. Look, in KNN algorithm, we learned nothing. You remember I told this that algorithm is a lazy learner because there is nothing to estimate. You have data and then you compare new instances with this data and no parameters are estimated. In this case, we estimate something in the model. We estimate these probabilities given our sample data. So that's where the learning part comes. But you see that nothing is difficult in this learning because we are doing all this learning throughout the whole course of statistics. We are doing this estimation all the time. Just one thing why we call this machine learning, because the machine must learn all these things and then apply this somehow. Okay, is this clear with these probabilities?
Yeah.
Yes.
So now the last step. Given that an email has a word Bitcoin, is this likely that this is spam or not? We need to calculate two probabilities. Well, yes, here marginals, P yes, P no, 5 and 95 over 100. So suppose the email with the word Bitcoin is received. We should classify this as spam or not spam. So we need to calculate two probabilities. Look, the probability that this email is spam, given yes, given the word Bitcoin, and the probability that this is not spam, given yes. So we know this information. We know that our email has a word Bitcoin. So this information is already given to us. Now, given this information, we need to calculate the conditional probability. What is the probability that this is spam? What is the probability that this is not spam? And choose the class with the maximum probability. So among these two, we choose which one is the biggest probability, and based on this, we pick the class to predict, to classify our email somewhere. So here, using Bayes' rule, here, probability that this is spam given yes is probability that this is yes given spam multiplied by the probability that this is spam divided by the probability that this is yes. We computed all these probabilities. Yes given spam is 3 over 22. There must be times, multiply 22 over 100, probability that we received spam, and divided by 5 over 100. And the conditional probability is 0.6. So probability that this is not spam given yes is, oh my god, it's not on the screen. This must be 0. Well, let's calculate. 2, 27, 28. So basically it's 0.02 divided by 0.05, 0.4. Yeah, because, well, these two probabilities must equal to 1, right? Must sum to 1. We have the fact that the letter has the word Bitcoin, and so we have only two possibilities, whether it's spam or not spam. So therefore, if this probability is 0.6, the other probability is 0.4, right? So And now we see that probability that this is spam is larger than the probability that this is not a spam. So what we predict, the likelihood that the message is spam, given it contains the word Bitcoin, is 60%, and the likelihood that it is not a spam is 40%. So our prediction is simple. We predict that this message is spam. Very simple. I mean, the most problematic thing here is to apply the bias rule. And once you know how this works, well, it becomes very simple to apply. Well, can you guess what's next?
STR.
What?
The next example, or what do you mean? Sorry,
No,
I
no,
thought
no, no,
you
no,
were
no,
talking
no.
for the next
I mean,
example.
how should we develop this method? Because now it seems very simple, right? So it's kind of like, okay, we have only one word, Bitcoin, and we predict that the message is spam based on one word. How should we develop this model? Look, we initially formulated this model in a way that we must have more than one predictors, right? So it's not only one predictor whether the message has a Bitcoin word or not. There are possibly more.
Maybe we multiply
No, 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 no,
or
no.
wait.
I mean, we want to expand our model to incorporate more predictors, or to incorporate more independent variables. Now we have only one independent variable. Look, in our case, independent variable is yes or no regarding the Bitcoin. This is only one variable. What if we include more variables? Like, well, there are some additional predictors that an email is spam. For example, like lottery word, or like million word, or something like I'm your uh, I'm your uncle from Nigeria, who is now kind of somewhere in the Atlantic Ocean and looking whom to whom to give like $1 million. You know, this kind of
It's a
letters
long one.
was very popular. I mean, there are some keywords that can give us a clue that an email is a spam. And this is very logical, right? So we want to include more variables that help us to increase the precision of our prediction. Because, well, 60% is still not that large probability. Okay, so we are still able to discriminate whether the email is spam or not, but we want to include more. So that's the logic, right? So we know how to classify an email if it contains only one word, Bitcoin. Our X takes values 0 and 1, 0 if it doesn't have a Bitcoin, 1 if it has a Bitcoin, and also our outcome variable has only two values, 0 and 1, 0 if it's a spam, and 1 if it's not a spam. So what if we, for example, we want to incorporate more keywords that give us a clue that an email is spam? For example, Bitcoin, million, and unsubscribe, or other something else. We want to solve the following problem. We want to calculate the conditional probability of A given B, C, D, A, and so on. So first of all, if we want to do this in the most formalized statistical way, we need to formulate a chain rule. And the chain rule will look like this. So because we want to have a joint probability of all these events happening together. And this joint probability is going to look like probability of A So the event A happens, multiplied by the conditional probability that event B happens given A happened, then probability that C happens given that A and B happened together, and then probability that D happens given that A, B, and C happened, and so on. So there is gonna be a huge mess now, because formally, if events A, B, C, and D are not independent, we must calculate this joint probability given this chain of multiplications. Like for example, what is the probability that you will call a random person, and this is gonna be a female, 20 years old, working, I don't know, working as the manager in a bank, like 4 characteristics. So how to calculate this probability, this joint probability, using the previously formulated conditional probability approach? We need to first compute the probability that this is gonna be a female. Then we need to calculate what is the probability out of all females. We know that this is a female. What is the probability that this female is 20 years old? Here. Now, what is the probability out of females 20 years old that this is a manager? C. And then, what is the probability that the person works in a bank, given that this person is a female, 20 years old, and has a manager degree? So you see that this becomes a chain of events. And this is useful to solve this problem. And we need to fit lots of these probabilities.
I thought you will say that if this is a girl, then it is more likely. Sorry, if she is a manager, that it is more likely for the person to be a girl. I thought you would say
Well,
that.
we can,
In
of
this
course,
example,
we
it
can
is-
reverse this. Yes, of course, we can reverse this, and A can be anything. Like A can be a manager. So it depends on the direction of these events. Yes, I agree. I totally agree. Because look, you can start with other logic. What is the probability that the person works in a bank? Then what is the probability that the person works in a bank as a manager? Then what is the probability that the person works in a bank and he is or she is a manager? And what is the probability that he or she is 20 years old? And finally, what is the probability that 20 years old person working in a bank as a manager is a female? It's also possible. Or we can do this in a completely different way. I ask how old is the person, like 20 years old. Then what is the probability that 20 years old person is a manager? What is the probability that 20 years old manager is a female? And what is the probability that 20 years old female manager works in a bank? Any direction is possible. Basically, nothing is wrong with this. But
no, I was talking. I was talking about the independence that her role of manager in the, for example, in the call center might influence her, like that she's a female.
Yes, yes. And that's why if we don't know about independency of events, we must act in exactly this way. Because if we don't believe that two events are independent, the only way how to calculate the joint probability is this one. So this is the most correct and most proper way to calculate the joint probability that the randomly chosen person is female, 20 years old, having the manager degree and working in a bank. Joint probability. So the first problem, so like this, and I agree, probably these events are not independent. If we know nothing about their independency, this is the way how to calculate this joint probability. But now, look, if we need to calculate this joint probability in the way that I described on the previous slide, it expands the computational time for our model, because we really need to compute a lot of things here. We need to compute how many, for example, how many females out of the total number of observations, then how many 20 years old females out of females, then how many how many managers out of 20 years old females, and so on. So there is going to be a huge mess in the computation. And once again, when the number of variables increases, when we feed there like 5, 6, 7 or more variables, that's going to be a huge mess. First. Second, the direction is not clear. So I demonstrated you 3 possible directions. We start with the gender, or we start with the occupation, or we start with the age, right? And so all these directions are possible because they are dependent. And yes, there is gonna be almost impossible to correctly estimate all these things. And that's why we need this assumption of independency. So this is an assumption. This might not be true in reality, but in order to simplify our calculations of this numerator, and the numerator must have this joint probability of events, in order to simplify this, we assume the independency of events or independency of features. And this is called the cross-conditional dependence. And this is why we call this classifier naive, because, well, that might be the first question. Why, well, we are using bias rule. Why is this naive bias? Because we naively assume that all events are independent. So, as Vlad said, we assume in our computations that gender and occupation are not related. So, if I know the gender of a person, I cannot predict anything about the position of this person and which industry this person works. If I know something about the industry that the person works, I cannot predict. It gives me no additional information about the gender of this person, or about the age of this person, or about the degree of this person, something like this. Here, how we explore this, how we exploit this assumption of independency, just throwing away all these features from the conditions for probability of C and probability of D. Yeah, so it's much easier to calculate these probabilities, but on the other hand, it slightly well, makes us makes our calculations so kind of puts the structure of this independency of the events. So let's see on the example how this would work if we include 2 more features. An email has words million and unsubscribe. So now look, we need 3 different contingency tables. So one contingency table is here with totals, another contingency table is here, and the third contingency table is here. But I put them kind of side by side. So look, this must not sum to some number. So look, we have 22 spam emails, And out of 22 spam emails, we have 3 with the word Bitcoin. And just to make a short notation, we will denote this as W1, so word 1. And 19 that are without the word Bitcoin. So then 11 spam emails contain the word million, and 11 spam emails do not contain the word million. So in total 22. 13 spam emails contain the word unsubscribe, and 9 of them do not contain the word unsubscribe, and so on. So you see that these are just 3 separate contingency tables, and that's where our assumption of independency helps us, because instead of making, I don't know what's that's gonna be, like 4-dimensional table with all these dependencies, right? So how many spam emails have together Bitcoin and million words? We are free of this necessity. We separately count how many emails are spam and contain the word Bitcoin, how many emails are spam and contain the word million, and so on. So that's where what buys us this assumption of independency. So now, suppose that we receive an email, and this email has words Bitcoin and unsubscribe, but does not have a word million. So we are here in this column. Bitcoin is yes, million is no, and unsubscribe is yes. So we need to compute the following conditional probabilities. We have an information about this email. We have 3 variables, W1, W2, W3, or X1, X2, X3, whatever. So we need to compute the probability. First of all, we compute the conditional probabilities of Bitcoin given spam and Bitcoin given no spam. So 3 out of 22 and 2 out of 78 here. Then we compute the conditional probability that an email does not have a word million, so no W2 given spam, it's 11 out of 22, and no W2 given not spam is 63, no million word, out of 78 here. And the third is that there is a word 3 unsubscribe, so 13 out of 22. This is the conditional probability to receive a spam with the word unsubscribe, and this 21 over 78 is the conditional probability that not a spam email contains the word unsubscribe here. So we compute these conditionals, and then we need to, in order to classify our email, we need to compute these conditional probabilities. What is the probability that an email is a spam given W1, no W2 and W3, and what is the probability that this is not a spam given W1, no W2 and W3. So yeah, it doesn't look very nice. Look, I put here P prime. You will see why. This is not an exact probability because of our assumption about the independency. So we assumed an independency, and therefore this is not going to be the correct probability now. So how do we calculate this? Based on our assumption of independency, we need to take these 3 conditional probabilities that we have calculated before, multiply them by the probability that the email is spam, and divide by the probability of observing W1, no W2, and W3 together. So what is this probability? Since we assume that they are independent, this probability is simply the product of their marginals. So let me go back. What is the probability to receive a word Bitcoin? Is 5 over 100. What is the probability to not receive a word million. It's 74 over 100. What is the probability to receive a word unsubscribe? It's 34 over 100. So we have these three probabilities, we multiply them, and we have this total probability that we will have word Bitcoin, no word million, and word unsubscribe here. And in the numerator, we simply multiply the conditional probabilities here. In total, we have 0.746 or 70.5% probability. But once again, I put here a special mark that this is not an exact probability because of our assumption. So the second conditional probability.
Maybe say that that's an estimate.
No, it's not an estimate. Basically, if you would, for example, go and read some books on the machine learning, well, first of all, as I said, most of these books are not very nice in terms of notation, because it's very annoying. So every book has different notation, different terminology, and sometimes it confuses. Second, most of the books and the algorithm itself, they don't even divide this by this p. They just compute the numerator, and you will see the reason why. So they just compute some object. I was trying to simplify this as much as possible, so therefore I just decided to go along the algorithm that we have discussed before. But in the books, the algorithm is slightly different. They don't divide this by the denominator. It's just some object. It's not an estimate, it's just some number, some likelihood to observe spam given all these things. It's our guess. The second conditional probability, which is not exactly probability, is 0.3457. So we compute this based on the same thing. Look, the denominator is exactly the same here. The numerator changes because now we take conditional probabilities to observe word Bitcoin, no word million, and word unsubscribe given node spam. It's here. And now look, what is the problem? Given these three facts about our email, that there is a word Bitcoin, there is no word million, and there is a word unsubscribe, there are two possible outcomes. Either this email is spam or not. And we have these probabilities, like probabilities, 0.70 and 0.34. What's the problem with these two probabilities? Why we cannot call them probabilities?
It is not one. They do not equal
exactly.
One.
They do not sum to one. And the reason why they do not sum to one is we assumed independency. We computed these probabilities in a wrong way. Like formally, they are not correct. What we must do, we must scale them. We must normalize them to 1 in order to have the sum equal 1. So therefore, yes, we have a problem. Under this independence assumption, their sum is not equal to 1. What we must do? We must normalize it in a following way. We take this number, whatever it is just some number, which probably represents the probability. But to make them the strict probabilities, we need to take this number and divide by this sum. And we have this 67%, 08. And this is our estimate of the probability. This is a usual correct probability. Why? Because its counterparty has the following probability, 32, 92%, which now sums up to 1. So that's why if you go to, for example, Wikipedia has a very nice explanation of this naive Bayes classification. If you go to whatever book about the machine learning, you will see that all of them calculate these two numbers, this number and this number, without the division by this p. Why? Because this p does not matter. Whenever you do this normalization here, just imagine that we haven't divided these numbers by p, w1 or w2, w3. Nothing changes because the numerator and denominator just they are not divided by some similar number. Nothing changes. So that's why in the algorithm they just throw it away. It's not necessary. But I decided to show this just not to confuse this you too much with all these unnecessary assumptions. Still, the last step must be done. In the last step, we need to normalize these two probabilities such that they sum up to 1. So what do we see? First of all, we see that our estimate of the probability that this is spam has slightly improved, because now, under given this additional information, instead of 0.6, our probability that this is spam increased to 0.67, which is nice. And second, given these three variables, categorical variables, we still predict that this email is spam, because the probability that this is spam is greater than the probability that this is not spam. Yeah, we classify the email as spam. So you see that we are using our knowledge from the previous semester, from the previous courses, and now we are able, with this knowledge, to create some new and interesting things. Now we are able to make some predictions. So several conclusive things. So first of all, there are different types of this naive Bayes classificator, and they are different in terms of this probability distribution. What we assume about this probability distribution. What we have seen today is the simplest case when all features of variables are binary valued. And this is a Bernoulli naive Bayes. This is the simplest possible. Only two possible values of x's, only two possible values of y. If our variables are categorical, but they can take more than two values, we use multinomial naive Bayes. There is just the idea is exactly the same, only instead of two columns in your contingency table, you will have 3, 4, 5 columns and so on. If y variable has 3 or 4 or 5 categories or classes, you will also have several rows in this contingency table. The logic is absolutely similar. Everything else works in exactly the same way. And finally, we know that axis might be continuous. In this case, we assume that these continuous variables are normally distributed. Again, some structural assumptions, as in statistics. And we use what is called Gaussian naive Bayes. So Gaussian, because the normal distribution is also sometimes called Gaussian distribution, after Gauss, who invented or proposed this distribution first. But again, the logic is exactly the same. This is out of the scope of our course, and so just if you understand how this works, well, basically, so Gaussian bias works in the similar way. So now, up to this moment, we have two classification models, and we know k-nearest neighbor classification model, which is a lazy learner and does not have much to learn. We know another model, naive Bayes model, which also, I think from the nature of these models, you see that, well, I would say k-nearest neighbors is more appropriate when your x variables are continuous variables, right? Just to measure the distance. And maybe it's not very nice when x's are categorical variables, and we discussed this last time. If you have several categories and if they are not ordinal, it's very difficult to say which distance is larger, the distance between the distance between banking industry and transportation industry, or the distance between the aircraft or airlines industry and the telecom industry, right? Whenever you have some categorical variables, it's very difficult to measure the distance between them. So that's why I would say that k nearest neighbor is more appropriate when variables are either ordinal, or ordinal, it means that you can put them in some strict order, like bachelor, master, or doctor, for example. Or if they are numerical. In case of naive bias, well, the categorical variables work well, and you don't measure some distance. Well, it's very nice. On the other hand, k and n is also possible to use for the regression models when y variable, when the outcome variable is continuous. But naive bias is not, right? Because you predict the class, to which class this goes. Yeah, so we use a simple bias theorem to calculate the conditional probability here. And so these both methods are very simple. You see that you can calculate everything with your hands. Basically, no need to kind of apply some complicated algorithms, even though it is possible to compute with the help of some functions. And later on, I will demonstrate you how this works in Python. But everything is we are able to illustrate everything with some simple examples and calculate this manually. Yeah, and next time we will have the last lecture on statistics. And next time I will try to prepare you one completely different method from unsupervised learning, which is called clustering, when we are trying to, let's say, search for some common patterns in the data. So when we don't know whether this data is, I don't know, grouped by some criterion or not, and we want to group this data automatically. Any questions?
So you said that naive bias is able to compute numerical.
No, in naive bias, the outcome variable y must be categorical variable.
Oh, okay. I just thought that you said it
because it's about no. The explanatory variable x's can be also numerical. Can be the variables, continuous variables. In this case, you will use this Gaussian bias instead of Bernoulli bias that we used today. But for k and n, y can be continuous. Yes. For nearest neighbors, y can be continuous. Basically, the idea is very simple. Just several words about what, because last time we somehow predicted y equals 0 and y equals 1 based on our neighbors. So how should we calculate y if it is the continuous variable? It's very simple. You take neighbors, like 3 neighbors. You know that these neighbors, like, I don't know, for example, you want to predict the salary of a person. You know that neighbors have the following salary, like 30,000, 40,000, 50,000, 3 neighbors, and then you calculate the average between these 3 neighbors. And that's how you predict the continuous variable according to the nearest neighbors method. That's simple.
Okay. And also, will we have like some home assignments? I just want to ask that the exams are coming, and if we would like to get our mark with our home assignments,
As I
and
said, so let's now look, guys. Yeah. So let me finish the recording.